Okay, thanks to be here. Okay, so I try to give you a panorama of the different fluid instabilities and structure, coherent structure, waves, vortex, when we working in our lab and related to different problem of physics. So, as said by Professor Sweeney, my main activity is experimental, so I try to give you an explanation of how we do in our experiments and our work. I am in the, so first of all, thank you a lot for the organizer to give me this opportunity to be with you. Really, I'm very happy and very sensitive to the interest of this particular school. So thank you again. I came from the École de Physique et Chimie of Paris. It's in Paris, in France, the engineering faculties in the university are normally in what is called the big school. Our is a small big school because we have only no more than 70 students, but many teachers and professors, and we have especially an experimental activity to produce physicists and chemists as engineering, and with a lot of innovation, but also a lot of history, because it's the place where Pierre and Marie Curie discovered radium, and they discovered radium essentially because they are very good experimentalists. In this picture you see here, this is the apparatus built by Pierre Curie to measure radioactivity, because after Becquerel was observed this first natural activity, he put an apparatus to try to obtain a quantitative measurements of the activity. And as this, with Marie Curie, they found a new chemical elements, but essentially because they had in their hand a very strong instrument. And this is very important to know this history of Pierre and Marie Curie. And also, with the school with Joliot-Curie, Frederic, Paul Langevin was the head of the school, as Pierre-Gilles Lejeune and other important scientists. I go to speak about fluid mechanics. I suggest you to take, I think it's not more than $10, this multimedia fluid mechanics CD with a lot, nearly 500 or 400 movies of the different fluid mechanics experiments and explanations. So many times I go to use movies and concepts from this very interesting activity doing for a lot of very good colleagues, many from our SPCI, to show what happened with fluid mechanics. First of all, remember NAVIER-Stokes equation for fluid mechanics. NAVIER-Stokes has special equation with a nonlinear part and a linear one, it's the Laplacian, with given the diffusive transport, and this nonlinear term giving you the convective transport on inertia. So it is important these two combination of linear and nonlinear phenomena go separate ways many times when you go to analyze fluid mechanics phenomena. Okay, remember an important point is the kinematical viscosity. What I remember is the dynamical viscosity divided by the density, and this is the reason. And the air is more viscous than water. In terms of cinematical viscosity, what we go to use many times, okay? So first of all, concepts about typical size, typical times, okay? When you have diffusive phenomena, in diffusive phenomena, remember that the typical distance is related to the square root of the time, and the prefactor is the kinematical viscosity. Kinematical viscosity is the coefficient of diffusion of vorticity. For this, it's very useful in doing problems, okay? So, and typical time is the square of the typical distance in your problem divided the kinematical viscosity. For example, you have a sharp profile of velocity. This profile goes to diffuse with this typical time and with this typical size. For the opposite, when you have convective phenomena, you have mixing by vortex, for example. In this case, you need to consider another time with its wheel, with the typical velocity and the distance with, by example, returning and vortex, the time of return of vortex. So with those typical times, we go to explore all the phenomena of fluid mechanics. And for this, if you take Navier-Stokes equation, you go to be adimensionalized with the typical size, with the typical velocity. You can find the Reynolds number, which is the product of the typical velocity, the typical distance divided by the kinematical viscosity. And this Reynolds number is no more than the ratio of these two typical times, the time of diffusion and the time of convection. By example, if the diffusive time is low, you have the low Reynolds behavior, okay, with more diffusion, and so normally is the smaller time give the dominant mechanism. With this small introduction, because I think there are people who was not came necessarily or don't remember the time of when you learn about fluid mechanics. Another important point in fluid mechanics, many times you have strong velocities, you have inertia, and you have separation, especially when you have an adverse gradient of velocity, so higher velocity, lower velocity, and you produce this kind of separation. This is a very important problem, for example, in the airplanes. If you take a higher angle of inclination of the wings, you produce this separation, and you have a problem with lift, okay? So this is an important problem in aerodynamics in fluid mechanics. So I go to use this separation in what happened here. Here I have a region of deep water fluid, and I go to use this to produce fluid instabilities. Why? Because I have higher velocity here and very low velocity here, nearly and slow motion. So I have the condition for the flow instabilities. If I grow the Reynolds number in this flow visualization in our water tunnel, I came back after, okay, you can show two important points. First of all, the recirculation length, the size of the recirculation, grows with the Reynolds number, grows. But in one moment, you have fluid instabilities. And this fluid instability, you observe this vortex with vorticity normal to the wall, okay? And what you can observe in another point, more intense as the vorticity, more intense the intensity, the recirculation length shrinks. So we have essentially this kind of behavior with the recirculation length in the beginning for the stationary walls flow grow, and after, in the end, is constant because you have this shrink of the velocity. How I can understand in phenomenological concept this phenomena? In the beginning, what happened? In the beginning, I suppose I have slow velocities, and the diffusive phenomena is more important. So if I have velocity here, by diffusion, the velocity came to this is the backward facing step, 8h. Higher velocity here, null velocity here. By diffusion, the velocity came from here until here. What time take by diffusion to came from here until here? Then this is the square root of nu t. But what is delta? Delta is this distance. What is the time? This is the time to go from here until the end of the recirculation length. So it is L divided U. So I put here inside, I transform with the Reynolds number, and I found that L, along the length of the recirculation length, grow linearly with the Reynolds number, what is I observe. So for this diffusive mechanism, explain me the growing in the beginning of the recirculation length. What happened in the end? In the end, I have strong vorticity. So the typical time now is the time to return this vortex. What is this time? Is the wavelength with the size, length, the wavelength, the size of the length divided 2, or the size of the vortex, divided the typical velocity, which is the order of magnitude of the free stream velocity, because I have free stream velocity and 0 here. Okay? So the typical time is this, and in this time I need to go from here until here, from the recirculation rate divided the velocity. So I observe, in this case, that L is proportional to H, so the L divided H is constant. So I have the two behaviors, a small Reynolds number, diffusive, a big Reynolds number, convective or inertial, but in the middle is the problem, because it's not very clear how is the law for in between these two states, and this is an open subject. On subject are very active. There are a paper last year from the group of Swiss how to understand the very nonlinear phenomena to take in consideration the two extrema. Okay, I speak about water tunnel. Water tunnel, it is not on top, it's not a tabular experiment, but nearly. It's the smallest water tunnel in the world. Normally, you have in your universities a lab of mechanical engineering, aerodynamics or aerodynamics, and you have a building for a water tunnel. First of all, we are in the center of Paris. It's very expensive, the square meter. So our water tunnel is no more than this half of this size. So a small water tunnel you can build in your institute, because if you have a workshop, it's only plexiglass. You have holes and plexiglass, no more than this. And it's very efficient because you do basic physics and you can do application. You can do, to study the phenomena of many problems, you can do small reduction models to study what happened, by example, flow control in the TGV, in the train of the grid velocity in France. There are not opposition, okay? So after I can help if you have ideas. There are another water tunnel with small in Long Beach University, but it is important. Important point. What you see in fluid mechanics. Attention. What you see not necessarily is what you exist. Bizarre. Why? Because one is the streamlines. Streamlines is the tangent to the velocity vector, okay? It is in stationary flows, no problem. What you see here with particles, with the trajectory, the stick lines I go to speak after, is what it is really the streamline. What is important is the velocity. After we use PIV, the method to measure the velocity, and we take pictures, and it's very important, to try to measure this tangent vector to the velocity of the flow, okay? But what happened, normally we put dye in one point. We put dye here. The dye is transported until here. If the system is not stationary, and each time this molecular of dye observes different motion. In one moment, this dye here was up here, but the particle here, this particle came from one time before from here, and this from other times shorter here. Each particle, which you see here, has the history from the exit of the dye until the moment you take the picture. It's very complicated. This picture is really very complicated because it's this integration of the past. Okay, there are an unstationary flow. It is called a strict lines. Strict lines is not streamlines. Remember this. Okay, this is a typical error of the people doing numerical work. By example, see up. Okay, try to show this. No, you don't show this except you put particles in your code and you follow the particles. Okay. But normally, if you like to see what happened, what you see in visualization seems similar to vorticity. Okay. The flow visualization was very old. You know, Marey was the people in this time, in the end of the 90s, he built this wind tunnel. He is the same guy who invented the cinematography. And at the same time, he was interested in studying the flow, to flow visualization. Okay, I come back to the backward phase step. What happened? The backward phase step, I have this profile of velocity, I have this inflection, I have this strong vorticity here here is the recirculation, the free wakes, okay? And this is I try to understand why there are these instabilities. This is some kind of shear instability, and typical example of shear instability, if you have two flows as this, you incline this tube, and you can see this typical Kelvin-Helmholtz instability or shear instabilities, okay? It is very typical in many problems of fluid mechanics. For example, many times you have this flow with this strong gradient, in the case of Poisson flow, in the case of Angette, in the case of the wake after a cylinder, the mixing layer. This is very typical. What you do to try to study this, you study linear stability. So you take the flow equation, for example, the 2D equations, you separate the flow in the basic state, and you add small perturbations. And after you take, as the perturbations are very small, you take linear approximation. That is the linear problem of the Navier-Stokes. You suppose that this perturbation has this normal form. What is this? It's an onde, if you want, with a wavelength, or wave number k, with 2p divided wavelength, and a frequency, imaginary frequency, real part, is if this part is this imaginary frequency here, with this is imaginary here, is positive, the flow explodes. It is what you try to see is the dispersion, the relation is the relation between the wavelength and the wave number, the wave and the frequency for each Reynolds number to see what happened. So what you do, you take the basic flow, you put in the equation here, you take this basic flow, by example, the mixing layer, or even this particular approximative basic flow, you do the dispersion relation, and you obtain this. What is this? This gives the growth rate positive, if this negative, the flow is stable, positive between this wave number and this wave number, the inverse of the wavelength. So it is. And there are maximum. So normally I expect to see this wave number or this wavelength. Remember, very important. Almost the calculation in these flows, if I do a tangent, hyperbolic tangent here, or this piece of this mixing layer, normally this value is 0.39, 0.41, very near 0.4. If you need the order of magnitude, remember 0.4 as the typical wave number. And as this, I go to the more typical problem of the vortex shading, or the more typical open flow instability, which is the Bénard-von Karman, because Bénard was observed this in 1908, and von Karman gave the theory in 1911. So before Reynolds number 47, nearly 50, you have two wakes, stationary wakes, behind the cylinder. But in one moment, from Reynolds bigger than Reynolds critical, you have this alternative vortex shading with emission of the vortex, okay? And this is the important point. This is the cylinder, an infinite cylinder, and these are the vortex, okay? The vorticity parallel to the object, span-wise, not string-wise. I came back this, okay? So this was observed by Leonardo, very nice picture of Leonardo, who was observing nature, and nature is a lot of this kind of vortex behind a bridge, and you can observe this by satellite because you have a small mountain and you have nearly a 2D problem in the atmosphere, and you can do the emission in the atmosphere with clouds. So what is? Essentially, you have an uniform profile. You have the object, the cylinder, and you have the wake, okay? So this wake go to produce this shear instability. And it is the instability. An important point, if you see here, there are a very small change in the basic flow by the existence of the instability. And this is an important point what I need after, okay? So I have an experiment in our water channel, okay, about with fluorescein as dye, okay, and you can see it is really a hydrodynamic horloge, a hydrodynamic clock, okay, because they are very clear. This is an absolute instability, very clear frequency, and with attention, the wake not grow until no. It is what you observe, what you see. But in reality, if you take measurements, the perturbation grow and after decrease. Okay? So, and the typical size, where the maximum, is the correlation length in this hydrodynamic instability. Okay? So, and in this case, you have the dispersion relation. I remember one point. Why there are a cutoff wave number? Because if the rolls are very big, by example here is small wave number, the shear is very small, so small growth rate. If the wave number, the wavelength is small, big wave number, you don't see the shear. So it is the reason there are cutoff and this part is stable. Another situation, by example, if you have no miscible interface between the shear, you have the cutoff is given by the capillarity, by example. So the cutoff is given by the capillary wavelength. But here, the cutoff is given by the geometry of the flow. Order of magnitude of the frequency, order of magnitude. Remember, the 0.4 is the maximum growth of the 0.4 is the wave number with the maximum growth. So 2p delta y. What is the typical size? The typical size of the shear is the half of the diameter. Okay? So you can observe that the wavelength follow the dispersion relation of the shear instabilities is the order of 8t. It is order of magnitude. So if the frequency is the phase velocity of the wavelength and the phase velocity is smaller than the velocity u, you arrive to obtain that the frequency is this value. Normally, the frequency is measured with the Strual number, which is the dimensionalized of frequency multiplied by distance divided u, is 0.12. It is not an exacted, but if you have an instability and you observe that the Strual number is 1, sure it is not a shear instability. Okay? The order in magnitude, when you have this typical Strual number of 0.2, you can do the calculation, so you can observe you are in the good kind of instability. Okay, the real Strual number is this. The Strual number grows in the beginning from this onset and after is constant, and it is a nonlinear oscillator with the wavelength proportional to the square of the amplitude, but the amplitude is proportional to square root to the distance of the onset. Okay, so you have the law of the frequency. It's important because it's an industrial application. Because if you put in your pipe, for example, a cylinder, and you take a capture of pressure, you can measure the pressure of the vortex shedding, and you relate the frequency with the frequency to the Reynolds to the velocity, so to the flow rate. As this, you have many many sensors to measure flow rates in the industry. But another big problem is, it is what we observe. We observe this frequency. But if you do the calculation of the linear theory, is this low. So there are discrepancies of you calculate the global calculation of the frequency and what you observed. And what is the reason? Because these measurements are calculated on the basic of the basics flow at each Reynolds number. But I say, normally, the fluctuation by nonlinearities develop what is called a zero mode. So a stationary modification of the mean flow. And this modification of the mean flow has a strong importance. If you do the calculation, as we do, many people, do the calculation, not taking the real basic flow, no, the basic flow estimate, but the mean flow, you obtain the good. And this was many years ago, Malthus suggested to understand turbulence, take the mean flows from and do the linear theory, but the modification. This is a very important subject of discussion today. And one important moment to observe that these nonlinearities are real exist is you see the recirculation length behind the cylinder. What happened? The recirculation length grows, as I showed you before, linearly with the Reynolds number. And afterwards, the instability begins shrink. And the difference between the length before and this length is the fact, as the perturbation grows, put an additional mean flow who stop the recirculation. And this is the more macroscopic effect of the nonlinearity. You can see this, okay? The strong reduction. Okay. One point about force. This vortex produces force on the objects, okay? You can estimate, if you take by Safman the moment of vorticity in the vortex street, and you can approximate, and you can see the velocity, the force is proportional to the derivative of the product of the circulation and the distance to the central line. So, bigger is the circulation, bigger is the force. Smaller is the distance to the central line, smaller is the drag, by example. But, by example, if you change the sign of the circulation, you go to change the sign of the force. And you are in the case of the fish, by example, propulsion, because has the emission of vortex, but unreversed by Bernard von Karman. It is the Bernard von Karman who produced drag. But now if you change the sign, if you change, in this case you have not more drag, but you have thrust, okay? And this is one mechanism to go to give propulsion. So, by example, this is the PIV measurements. We have this drag. We have a flap, and the function of the frequency of the flap, we can modify the distance between the street, and when one moment the street is zero here, as in Kolmogorov problems, okay, and you can change this. And this is interesting because what happened? Many birds have a Strual number calculate about the amplitude. You take this amplitude of the flapping, okay, and multiply by the velocity and divided by the period. Almost the birds are around 0.2. And what happened? We have measurements with some flap, okay. So we have, in this kind of frequencies, we have Bernard von Karman, but we can observe for higher frequency this reverse. And this reverse, we can measure force, and this is the line which goes to change to drag to thrust. And this is the line to Strual 0.2, as the Earth observer. Okay. I speak about vortex shedding, about if you want, two-dimensional objects. But what happens when you have the vortex shading become behind 3D bodies? By example, a sphere. I go to my water channel, I put a sphere here, okay? And we try to study what happened. First of all, I compare the 2D problem to the 3D. In the 2D, we have two recirculations. In the case of the sphere, I have a torr of recirculation, an azimuthal recirculation. In one moment, this azimuthal recirculation loses symmetry. One part of the torr, by example here, is bigger than this part of the torr. And this go to produce two counter-rotating vortex, stationary. So the first instability in the case of a sphere or a disk are the existence of the breaking of the planar of the axisymmetric symmetry. And I produce two counter-rotating small, very weak, two small vortex, okay? And after we have, this is the situation, for example, in the case of the sphere between 212 and 270, this stationary instability, and after we have vortex shedding in the form of hairpins, okay? And this is what you observe. This is the typical hairpins, okay? So if you can from the side, from the top, or you can see in front, okay? It is the typical vortex shedding. One important point for fluid mechanics. What is important in the hairpins is the legs, this part, because these legs go to mix it very well. The head of the hairpin seems not very important. I see seems because it's a very strong discussion today. Okay. Okay. To give an idea what happened, perhaps you can see in the drops in spark water. Imagine a bubble. It's a sphere. I suppose the bubble is rigid. So in the beginning, the bubble grows, the Reynolds number grows until 212. And appear the two counter-rotating vortex to produce lift. So this lift put an angle. So the bubble arrive here and deviate here, stationary. And after, there are the hairpins. So I have the zigzag. And a high instability is this kind. So you can observe this when you have and drop this sequence of instability. Perhaps you can observe this in a bottle. Okay? Good. And then, it's important because I come back to the head. Now we have experiments when we turn the sphere, because the interest is to study the wind turbines, okay? So, but it's very similar, okay? The interest is, and what happened here is, okay, is if I put rotation, I add vorticity at one of the legs and diminish the other. So the hairpin disappears and you have an helical mode. And almost the situation, the hairpin is very short region and you have different helical, higher order helical modes. Okay, good. Attention. What I explained is valuable all the time for all the shear flows? Not. Because if I apply this concept to Poisson flow, plane quet, pipe flow, even boundary layers, what happens is you can calculate the critical Reynolds number, and it is a critical Reynolds number. By example, in the case of wet plane, say all the time is stable. In pipe, all the time is stable. But the reality, you can observe other critical, you can observe transition are Reynolds less than the linear one, even if it all the time is stable. And it is why, because exists subcritical transition to turbulence with the existence of very localized structure, with the spots. It is one spot in our channel, okay? With these spots are essentially with string-wise vorticity, no span-wise as the Maynard von Karman, okay? And it is sensitive to finite amplitude perturbation, okay? So in the case of wall-confined shear flows, we have different situation. And why? Because if I am wall, I have strong gradient, the string-wise vortex in the direction, go to mixed and put the high momentum from here until the wall and the opposite. And it's not the same scenario I discussed at the beginning with the Maynard von Karman. And this is the reason why you have a very different situation, even when you have shear, but the existence of wall bonded, okay? In this case, now we do an experiment to produce Couette Poisson instability. So we have a moving belt here and fixed wall here. The Couette put water from one side to the other side, came back, and we can see laminar, the existence of spot, the existence of band, or the full turbulence here, and this is what one of the subjects to understand the existence of these kind of transitions, okay? Another important point to the string-wise vortex is what occurs also in reality. By example, take objects as your car. You have behind this part, you have a span-wise recirculation, but as the sphere, as the disk, there are many very strong string-wise vortex behind your car. And these very behind are weak of singulation. But they're important because 45% of the drag, the pressure drag in your car came from the vorticity you have behind. So it's important to modify this hydrodynamics. And for this, we can put counter-rotating vortex in vortex generators. For example, we have here this solid vortex generator who go to produce pair of counter-rotating vortex, who go to interact with the body to modify these big structures, and has a very important effect. Normally, you cannot use this because it's not useful in a car, but you put jet in across flow, you blow, and this jet produced two counter-rotating vortex, and this is what is today the vortex generator applied in MEMS, in very small apparatus. Okay, to finish, I come back to the Kelvin-Helmholtz instability, shear instabilities. I say before the cutoff was given by the size of the boundary layers, but you can, if you have an interface, the capillary effect try to don't like to put very small radius. Okay, so I go to show you an Kelvin-Helmholtz instability and shear instability, but with interface. But in this case, I go to produce this in the following. I have two flows here, no miscible, water here, and in the top, very, very viscous oil, and I try to produce this oscillation. And what happened with this oscillation? I go to generate Stokes layer. So you know by skin effect, when you have rotation, in proportional to the frequency, you can induce a wave boundary layer here. Inversely proportional, higher is the frequency, small is the thickness, okay? So if I can produce this, now I have a shear instability, even the function of the time, and this shear instability go to produce the frozen waves, okay? And it is what, an easy phase, what is the reason? Because one of the oil here is very viscous, very big wave boundary layer, so it turns with the reservoir, with the box, and the other not. So it is equivalent to shear one layer, shear the other, but it's nearly no motion. Okay, it's very easy to do. Okay, if you take this and you go to observe what you have here, perhaps after you turn, okay, and you can produce. We have here 2 liters of this oil. If you want, you take to come back to your lab and do this small toy to show you this kind of surface instability with Kelvin-Helmholtz. It's interesting because with this kind of instability, you can see the linear phenomena, the non-linear, the saturation, and even the very interesting problem of wave breaking. By example, if this, you remember the finger doing this kind, it's very similar to the problem of wave breaking, and we study now how is the typical distance in function of time and compare with the recent theoretical prediction of Poumon. And you can do even the same with sun, okay? You have sun, water, and you can do this, but in this case it's not shear instability, but you arrive to produce underwater dunes by modulation of the interface with the same concepts, okay? Good, I think as this you have an idea of what you can do in flows, even if they're not exactly tailored experiments, in many cases, yes, but I suggest you to build your water tunnel in your laboratory. Up to finish, I am very happy today, even with emotion, because I was studying in Argentina, in Buenos Aires, and one of my teachers was Giambiasi, and here we are in the hall of Giambiasi. So really, I am very committed. He was a fantastic teacher, and he is very recognized. It's just this hall of lecture as the Giambiasi Hall. So it's a good moment for me. I was the student here. I was Giambiasi, my teacher of thermodynamics, many, many years ago. Thanks to all my collaborators of the laboratory.